we completed it until this first part, like the linear regression to this model. Um, okay, I downloaded all of the data, and then my first idea was I don't know, I'm not sure how good of a tool will like be linear regression for doing this task. But anyway, I will try to do it first and see what kind of results I can get, and then from that point, see what kind of pre-processing can I do the for improving the performance. So basically, I implemented this formula we see here to obtain the beta matrix, and as I told before, I couldn't get like because the we have so many like linearly dependent columns in this matrix, we couldn't make the transpose. So I used the pseudo inverse to do that, and then I compute the beta, and I did the predictions with this model, and the accuracy was very low. Then I think this actually says that I cannot predict anything. This might be just be some randomness. And then I did some plots.
Let me see this. Let me see this. Let me see this. Because I think from this we can understand some things, right? Go ahead. Tell me the story that this plot is saying. Yeah?
Okay. So I think that because of the way that the predictions are being made, like
no, stay on them. Oh, okay. But stay on the matrix a second. Stay on the matrix a second. Go back to the matrix there. You see that you could do some simple operation. So I don't know if there is an error in the coding, right, or just in the representation. But you see that this matrix is telling you that if your network predicts a 1, then you should change the prediction to a 0. If your network predicts a 2, you should change the prediction to a 1. Is this correct? You know what I'm saying, right?
Yeah.
So is this what is that what you're telling me, that if you just relabel the prediction of the networks without changing anything, you will improve your accuracy? Is this what the network is saying?
I think it will improve the performance, but I wasn't really thinking about doing that because I think more the problem comes from the root. Like this will be just a part of the solution to my actual problem.
No, but this is not completely nonsense, right? So, for example, look at the error, right?
Yeah.
In predict, because the top, yeah, exactly. That one that is saying that that the 1, it's most easily confused for a 1, a 2, a 3, and a 4. So there is something strange there, right? Because 1, 2, and 3, right? They don't behave very similarly, right? But you can see how a 2 and a 1 are very, very similar, right? So this goes to the discussion that we were having, that think about the L2 distance between images, right? And then think about the L2 distance between the average of all ones, the average of all twos, and so on and so forth. Changing the label of the prediction, right, will change the performance, right? Is this clear to you,
Yeah.
Francisco?
Yes. Okay. So then I look at how much, because I saw this prediction. I thought, okay, maybe we can gain some information by seeing how spread out are the results.
Very good. Very good.
What I do is basically I get the coefficient. I get a whole sum, and then I get the predicting label like that, and I see that there are not separate groups, and there is no linear relation between this. Like we would expect to see all of the 1 values here, and the 2 here, and the 3 here, but I don't know how much I can really tune out this to really be able to say, okay, I will limit the range, or I will set some bias to be able to like how can I say narrow down this target. But I think that approach will work very well. But anyway,
just stay there. So is everybody? Yeah, I hope that everybody got this, right? Because I hope that everybody got this part, right? So because the prediction, So because the prediction, your predictions are continuous predictions, right? And then you have to convert them to discrete prediction, correct, Francisco? So this is why, right? Can you stay on that plot? This is why, like,
it's a little bit laggy, so
okay, sorry, okay, no problem. No, maybe I'm laggy for
okay.
me, yeah. Yeah, you can see that what you would have expected, right, will be a linear relationship between the prediction. I mean, the model is enforcing a linear relationship between the input and the output, but then if you try to check the distance between labels and predicted values, right, you see that the continuous prediction over the predicted labels does not cluster as Francisco said it, right? You would like that that when you do this thresholding operator, so that you take the continuous prediction and you bring it to a class, this will correspond to a linear. Go ahead. Very good, Francisco. Very good. Keep going.
Okay, so here, so I don't know why it's so laggy now. So here we have another plot, and we can see that maybe we can see more clearly here how we have kind of a line, but it is not as pronounced as we would like to have a more clear classification for the labels. So then I thought we have some suggestions in the document. One of them was convolutions, rotations, Fourier transforms. So because I didn't know anything about Fourier transforms, I said, okay, maybe I should let that for later. But I think now that I should watch more about this. Maybe this is the way to go. If I want to get some better accuracy with this model. But I thought about convolutions, so I think this is like easier to implement. So, spoiler, it didn't work that well, but I should show it anyways. So here we have like some set of random images and different kind of alterations that we can make, like using some. But because every one of these images has, in the end, it's just metric with values, and every pixel has its own value. So by doing some operations with it, which are called convolutions, we can take like run kind of something that we call a kernel over all of the pixels and modify it according to the values we assign to this kernel. So these are some basic operations that we can make, like opening, closing, Gaussian, edge detection. I'll use kind of the same methodology, which is setting a kernel and applying that kernel over the image. Like saying very simply is like setting a matrix with some parameters and running that matrix for every pixel of the image. And I thought that, okay, maybe if we use the image as it is, as well as like without any processing, is not as effective as if we have these eroded images. Maybe these kind of images can give us some better accuracy. And later on, I tried that. So I made a copy of the dataset and tried to predict it, but I got worse performance. So I only got 10% of performance, which is absolutely random. So even if my model was taking out, like, I will get 10% of accuracy anyway. So let me see here, like all of
everything get predicted like 4 or 5. Yeah, it makes sense.
Yeah. So my conclusion here is that my model can take any information. Like having this kind of images is just like he can even recognize any number here. Like the way the model is designed, it doesn't have any meaningful information for it. Like it's just like noise. It's like that plugging noise into my model. So the next thing I will try to do is now.
So just a second. If you go back to the matrix, right, you see that what your model is predicting. The prediction
Here,
one.
here.
You see that the model is predicting the average, right? Because the average is 4.5. It moves to 4.5.1. It gets a 5. A 4. Gets a 4, and so the prediction is always just the average, right? So this happens when the model is not learning. It just learns to predict the average, and the average value is always 5. So I think here you're taking an L2 distance between the prediction and the true label. So the model is just producing the label 4.5 because it's the average of the data set, right?
Yeah.
It's the average of the labels. Go ahead.
So the next step will be, I will try to get some more accuracy by seeing what kind of useful information I can take from the Fourier analysis. I also talked about taking the PCA, but I think in this case, again, because of how my information is, but because of how my my features are taken off the data. I don't think it will be very useful, so I will go ahead with the Fourier transform, like Fourier analysis.
Very
And
good.
that's
Very
what
good.
we have going on.
Yeah, very good. Very good. Anybody else on the group has any comment on this? Yeah.
I don't know if there someone else that wants to share something with us. I think Francisco just did most of the work until now, so yeah, I think that's all from our part for now.
Very good. Very good. Yeah, so many things to think about, guys. I think so. The other thing that I told Francisco is that to check the numerical stability of the matrix inversion, because as I said, like I just would like to convey to you that the issue of a numerical stability of inversing this matrix with 7,000 elements, it's usually very tricky, right? So it's usually very unstable. So check them on there. You can check. You can do that by checking the prediction between the sklearn model, sklearn model, and the one that you do yourself. Okay, very good. Next one that wants to tell us about something.
I have a question about like challenge 1, because I was in the one Shitong group of challenge 1, and we said we wanted to present also this week because we didn't present last week.
No problem.
Or like we uploaded also a video. I mean, it would be quite the same if we present it now. So I don't know if we have to, like, we can present it. It depends on you if you want or not. Like,
let's do this. Let's finish the challenge 2, and then you guys present quickly, just for everybody to.
Yeah. Okay.
Because it's also a skill for you to present. So let's do that.
Mm-hmm. Okay.
Yeah. Next group. Who wants to go next? Elton, who's missing?
I think it's group 4. Is Joyce here? Joyce Wong.
Hi, I'm here. Can you hear me?
Yes.
Okay. So me and Iris will talk about challenge 1 first.
Okay. What was the group of your name in challenge 1?
Here's a group down.
Okay. Just a second. Is there anybody else that has to present challenge 2? Because then I think we take a break, we walk around, and then we come back for the presentation for challenge 1. Is there anybody else from group 2 that for challenge 2 that has to present? So let me check. So
my group has not presented yet for challenge 2.
So Joyce, would that be okay if you do challenge 2 and then we do challenge 1 after a small break?
Okay. So our group have 5 people, and everyone is active and talk on the Slack. However, we have some issue about the lack of prompt responses, and it has led to delays in our decision making and progress these 3 days. So right now we have finished the task delegation, and so we separated the challenge into linear regression. That is, Jean and I will work on that, and also the KNN implementation. And there's one people who will be in charge of KNN, and another group member will be in charge of slide and presentation. That would be our progress until now.
Okay, guys, it's already 8:30, so let's take a 10 minutes break. You walk around. I'll tell you. You walk around and you drink some water and you do some couple of squats, and then I'll see you back in 10 minutes. And then then we talk a little bit more. Okay. Ciao, guys. See you in 10 minutes. Cosa?
Dum, dum, dum.
She's like, I'm gonna hit you with the stick. I don't know who touched her. Ehi, ehi, ehi.
Bastonate.
Perché mi vuoi dare le bastonate, Titi?
Dum, dum.
Perché vuoi darmi le bastonate?
No, credo per matti.
Ok.
Dove è il gatto?
Il gatto? Che gatto? Non c'è il gatto.
Cappa.
Ah, è qua il gatto, vieni, vieni. Qua c'è il gatto, vieni.
Gatto qui. Gatto loco. Gatto loco.
No, 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 niente, no, niente acqua, Titi, vieni. Sì, c'è l'acqua. Sì, però andiamo a casa, adesso andiamo a casa.
Non ci c'è il gatto loco. Dove è il gatto loco?
C'è il gatto, dov'è?
Mm.
Dov'è?
Dai bastonate.
Perché vuoi darmi le bastonate?
Io, po.
Perché vuoi darmi le bastonate?
Io,
Titi, perché vuoi darmi le bastonate?
bam. Bam.
Bastonate.
Like to hit someone with a stick, it's a bastonata. So you want to give me...
It's one word.
Yeah, bastone is the stick. Bastonata is like to hit somebody with the stick.
Bastonate.
Perché?
Io bastonate.
Perché vuoi darmi le bastonate?
No, bastonate, io.
Io ho paura. Ho paura di questo bambino. Io.
Gatto.
Gatto loco.
Andiamo. Gatto.
C'è il gatto? Sì, è bello il gatto. Andiamo.
Gatto rotto.
Gatto rotto. Andiamo. Vieni, Titi.
Loco, ciao ciao.
Gatto, ciao.
Gatto, ciao ciao.
Gatto con la nonna.
La castagna, Titi? Ok, andiamo che andiamo a casa a mangiare la carne, dai.
Vediamo cane.
Sai che il papà...
Polonta. Polonta.
Ok, polenta, vuoi mangiare polenta stasera?
No,
Andiamo.
bastonate.
O bastonate. No.
No!
Andiamo, di.
Bastonate papà. Io c'è polenta.
Andiamo, Titi, dai.
Aia.
Polumpa.
Un palumpa, cosa hai detto? Un
We can
sasso. Vieni, Titi, che andiamo a casa a mangiare la polenta. Dai, vieni. Joyce, are you here with us, Joyce? Joyce can talk to me, Joyce. Joyce can talk to me. Joyce. Hello, guys. Can we go back to work? Is everybody
Yeah,
back?
for sure. We are ready here.
Very good. So yeah, is Joyce here? Can Joyce talk to me a second? Mm-hmm. Joyce, I know you're here. Did she drop out? No, she has to do the presentation for 2, right? So Joyce,
Can you hear me?
tell us, Joyce, because the TAs said that you want to drop off of from your leadership position. Just tell me a little bit what was the consideration, yeah? Just tell me what is the experience so far.
Or you mean why would I want to drop out the leadership?
Yeah. I'm not blaming
yeah.
you, right? I'm just curious. I'm just curious what was the experience for you?
I think I want to collaborate with other leaders as well, and overall the leading position has been. I think the experience is good, but there has been a lot of responsibilities and also some pressure. Therefore, I think maybe I could try to experience different roles as well.
Is that very tough to get everybody? Is that we have to spend a lot of time trying to get everybody on the same pace? Is the communication overload? Is the communication load very, very high?
I think it depends. Sometimes it's easy to get everyone on the same page, but other times it is quite difficult to get people to respond on Slack.
Let me ask you a question. Is there a clear difference between the attitude of Taiwanese students and foreign students, or you don't notice any particular difference there?
I'm not quite sure, but for some exchange students, they only take maybe 2 courses, and they could spend a lot more their efforts on this project. Well, Taiwanese students, they often have more credits to take.
So it's a good point.
It is harder for them to contribute as much.
Thank you for telling me. That is a very good point, right? It's a very good point. I think it's very bad that the students are taking so many courses, right? Because then they end up not learning anything. And, yeah. It's a good point. It's a good point, Joyce. It's a good point. Okay, very good. So should we do challenge 1 for 万事通?
Hi, we're here. So
Go
I go gonna present my screen. Yeah. Can you see the screen now?
Starting. I see myself. Okay.
Okay. So last week we were
Actually, Victor, I think we can just do our presentation. You know, we're the
I just want to point out some
yeah,
things
sure,
about
sure.
the code that
Okay.
we were stuck here in the part of developing the classic KNN algorithm because it was taking too long. So as professor suggests, we take two focuses on how to solve this issue. One was the Val3 version and the other one was the KD3 version. So for these two type of algorithms that fortunately it was already included in the library here, you can just select the type of algorithm that you're going to use for making the KNN algorithm. And we have the 2 versions, and it was like 15 minutes for the whole data set.
Very nice.
We didn't use the sample that consists in just 5,000 rows but instead we use the full dataset, the test and the train, both in the full 900 and something thousand rows. So we get the results very quick by using these two algorithms. That's all the major changes that we have implemented, and then the rest goes smoothly. So maybe we can just skip to the presentation to make this very brief.
Up to you guys. Up to you. You guys tell me what you want to do.
Can you present, Julius? Your screen?
Sure. Let's see. Where is the PowerPoint? Okay. I will actually also turn on my camera. It's always better to see a person behind the screen.
What a
You see my
hair,
screen?
Julius! That's a heck of hair. Congratulations! Your mom must be so proud of your hair. Yeah, go ahead.
Can you see my screen?
Yes.
Yeah, okay. So this is our presentation of predicting asteroids. Challenge 1 presented by the group Wan Xing Dong. Okay, the first task was exploring the data, and we immediately saw that there are too many features, and so we asked the question, which are the most useful ones for us, and we answered that question with printing out the correlation matrix, and it's a quite simple way to do it, but like then we saw which like in the top picture you can see which features correlated the most with the class, and then we used just these features, and there were like 6 features or something like that, and then I printed out it again. That's the middle picture, and there we saw that there are some features that correlate like with 1, so they are like same. So we could even reduce them even more, and that decreased the computing effort actually a lot. And after that, we split the training data, and we split the data set into 80% train and 20% test ratio. And we also one hot encoded the categorical columns, and that you can see on the bottom right. What does it mean? Like, because normally label encoding, that was the first thing I wanted to do, like that came into my mind, because like machine learning algorithms can just work with numerical numbers, and so like the categorical names can't be used, and I wanted to do that, like just assign the categories to one number, but that's not that good, because they have like some sort of correlation actually between them, because for example the 2 is like, or the 3, the broccoli, like 3 is bigger than 1, and the models, the machine learning models, like include that like that relationship between the numbers as well, and so it's better to do it like the one hot encoding. And yes, and then we also sampled the data to make it even more efficient. Then we went on to task 2, and to implement the classic KNN, and we used the KN neighbors classifier from sklearn to fit the model and make the predictions. And we used then also, like Victor already said, the ball tree and KD tree algorithms to optimize it even more. And then the result should remain the same, but it should be a faster computation. But it wasn't actually that. On like, at least on my collab version, like I like executed them both, and the classic one was actually faster, and I was kind of curious why it is like that, and I asked ChatGPT, and ChatGPT was like gave me the answer that it can sometimes be less efficient if there are too many features, or if the or if the second one was what was the second one? I have it written there. Ah, yeah, exactly, the imbalanced data, or if the data is really imbalanced. So if our data set was really imbalanced, like the most classes were MBA, I think, like the most asteroids were MBA. So there could be a reason. I don't know. Like it was that just ChatGPT said to me. So yeah.
Always believe ChatGPT. Yeah.
Exactly. And yeah, here you see the confusion matrices between the different Ks, K2, K4, and K6. And yes, like there was one special thing actually. I was like I saw and I didn't understand it first, but then Victor came with a quite like good solution why it is like that, because like I first said, the MBA class was in the full data set was like the most common one, the most used one class, the most used class. But here we have like the ATE as the most used class, and this is why this is because we cleared the data out. Like we cleared a lot of data out where we cleared all the rows with NA values, and so then probably the ATE was the most common after that. And here you can see then the ROC curve and the learning curve of the classical KNN, and the ROC curve shows us how that shows us how well the class was predicted. I think actually, like how good the classifier was for the classes there, and the diagonal line shows like a random classifier, and that means it that would be like the line if the classifier was just random, picking between like yes it is that class or it's no it's the other classes. So yes, and on the right side you see the learning curve, and there you see the training score and the cross validation score. The training score is the accuracy that the model achieved by just using the training data, like the training data also like testing data. And the cross validation score is when the training set was like divided into partitions, and then like always use some partition as test data and some partitions as training data. And like I wanted to print out also the learning curve of the testing data, but I didn't manage to do so. I like so far I didn't manage to print it out, but this would be also kind of interesting. Okay, Victor, then it's your turn.
Yeah, for the weighted KNN algorithm, we actually use a reduced version of the dataset. We just take 5,000 rows randomly because it was too large to work with this full model. So the execution time was like already 2 hours and still didn't give us the results. So we just take the decision to just work with a sample of the dataset. Can you skip to the next slide, please? So these were the results that we compared. In this case, I don't trust very much these results because it was just with a sample of the dataset and
like
gives us gives us almost similar results for the weighted KNN and for the classic KNN algorithm. There is not too much different for these very few data in the dataset. Can you shift to the next? Yes, you can see here we also print the learning curve of the KNN, the weighted KNN, and the classic KNN. The values approach to 1, but never become too close to 1. Like as we can see in other teams models, because for this case, as I say, I just use a sample dataset. If we were working with the full dataset, maybe we'll get values closest to
one more digit of precision, basically.
Perhaps 0.96, 97, something like that. It's not too precise because it's just 5,000 rows from the 900 or something like that.
Yeah.
It's very small. But still, uh, uh, I don't know if I can say accurate, but it's still a little bit closer to the one that closer to zero, even if the data is very few, because the training of the model was with 20% of the data. So once get the training completely, we can just start making the predictions with just few data. Okay, next to the following slide, also we print the receiver operating characteristic for the weighted and the classic. As Julius explained it for the previous model, this is like the diagonal is just like selecting randomly the things. We can see that they get closer to one in this case, like very
Yeah.
at the beginning. Yeah.
So is the
The
ROC clear to everybody? Yeah, everybody understands the ROC. I mean, because the labels are there, like true positive rate and false positive rate. So I think it's clear for people. But yeah, notice this is
Okay.
something that the statisticians they like to do, right?
Yeah, yeah.
It's a natural trade-off between type 1 error and type 2 error, right? And
To measure
yeah, go ahead.
the performance of the algorithms.
Yeah, because the easiest
There's-
thing is to go from the point 0, 0 to the point 1, 1, right?
Yeah.
Because if you always predict the one class, then you do a 0 error in one class and 1 error in the other one, and then the opposite is there. And what is difficult is to live on top, right? So you always want your curves to be pushed toward the ceiling, right, or the 1, 1 line, because you have always true positives and you have 0 false positives. Yeah. So go ahead. Yeah.
As you can see, for some of the classes, we get more accurate results. As you can see, for the class TNO, we get 1.00, but for other classes like ATA, we get like just 0.5. That's because maybe in the dataset that we take randomly, there were not too much of these classes to train with, so the results were not very accurate for these classes. Perhaps also because they were not balanced at the beginning at all, because they were the most rare classes, so the model cannot predict it correctly. That's one of my theories about why we are getting these results. Like very accurate for some classes, but not so accurate for some classes. If
Due to
you
the class
can,
imbalance, right?
yeah. For CAM also is 0.50. So maybe it's just almost a select randomly if is this class or not. It's not more like a prediction. So maybe the classes are too rare, or in the full dataset, even the classes is very few compared with the other classes. It's very unbalanced because MBA I think was the most common class. So we can skip to the next slide. Yeah, there are techniques to regularize, to balance the classification. So the two methods we have implemented is class weighting and custom distance metrics. We can skip to the next slide. Yeah, the class weighting is give more importance in the model to the underrepresented classes. Yeah, this allows us to ensure that the model uh, do not get biased to the classes that had more data. Like for example, in this case, the MBA class. Yeah, and here says why is weighting, because we assign more value, more importance to the data that has to the class that has very few entrants in the dataset, um reduce the value of those way more entries in the dataset. So it's is inverse to how many data of each class we have in the dataset. So we go to the next slide, please. The custom distance metrics. Here is apply a penalty term to reduce the complexity of the model. But also there are other that we actually don't implement. We can go to the next slide, please. Yeah, these two regularization technique was not implemented. For example, the undersampling or the oversampling. Uh, the undersampling involves removing sample for the majority class of the dataset. For example, in this case, if we have, for example, let's say that we have 600,000 of MBA, the rest is just 3,000, 10,000, something like that. We just get rid of the class that had more entries in the dataset to balance with the rest. But this can this can make us to load that much data. So it's we discard this technique. And also the oversampling involves duplicating samples from the minority class. This just means that if we have some classes that are very rare, we can just start inventing the entries in the dataset, but this introduce noise to the dataset. So we discard these resample techniques. We can go to the next slide. The cost sensitive learning. Yeah, in this case, it's like applying penalties or assigning cost of misclassifying certain classes, especially the minority ones. As we can see in our results, there were classes that get just like 0.5 accuracy. Uh, yeah. Why we don't implement these techniques? Because it was too complex and the model is already very complex, so applying this technique will just increase the time of execution and we are not going to get results faster as we desire. Yeah, so that's why we didn't use these regularization techniques for the model. Yeah, we also face challenges that we were only two people.
Exactly.
Schedule is different, so maybe we just uh, did all the work asynchronously because I just make a part and say, okay, I did this. Julius, okay, I gonna do this part or correct these results or see what can I do to get the results accurately. Then just work like that, but still getting the full work done. So I think it's okay, even we have these problems. We still meet. It, it says in nearly no meetings, but actually we meet two times, like Google Meet to discuss some
Physically,
for
yeah?
making the presentation. Yeah.
No, online. We made like online.
No,
okay.
yeah, online, Google Meet.
Mhm.
Very good, very good.
Yeah, yeah.
Okay, very
To
good, guys.
discuss
Very good.
how to do the presentation. Yeah. And also the thing that caused us the more was to actually learn some concepts like the regularization techniques. We have to Google search. We have to ask
Of course.
ChatGPT to explain us because it's the first approach to these concepts.
Of course, of course, of course. Very good. Okay,
Yeah,
thank you guys.
you.
Thank you guys. Thank you
Thank
guys. Joyce, I think you come back and you tell us about challenge one from the Quetzalcoatl group.
Wait a moment.
No problem. Para, 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 pam.
Okay, so This is Joyce from Group Hotel, and today we will be discussing our project on asteroid classification using the K nearest neighbor algorithm, KNN. So the objective of this project is to classify the class of asteroids based on their features using the KNN algorithm. For this, we use a Kaggle dataset, and this dataset has over 950,000 entries with consisting of 45 different columns, each containing specific properties related to asteroids. Here are a few of these columns. Before applying KNN, we need to pre-process the data. First, we drop the relevant columns such as name, ID, prefix, etc., and also columns that contain stigma, because it will not contribute to our analysis. Additionally, rows containing missing values were removed to ensure data consistency. Well, we also addressed the issue of data encoding by converting string and character-based data into integer types to facilitate processing. Okay, this part is for data visualization, and this pair plot would help us to see the distribution of these classes, which allow us to see the relationship between different features and how the classes are distributed across them. Each color corresponds to a class in the dataset.
Very cute, very cute.
Moving on, we applied logarithmic normalization and standardization to bring all values to a comparable scale. By dividing each data point by its standard deviation, as shown, I think it's here, it's standardization, and it would help us to enhance the feature comparability. We then use a correlation matrix to assess how different features related to one another. This triangle here corresponds to the data before standardization and logarithmic transition. And this part here is after we do the processing. You can see that after we do the processing, the correlation coefficient between certain features improved, meaning that relationships that weren't as clear before the transformation became more pronounced. For instance, the feature N and AD, they have a near zero correlation before, but after processing, it became negative 1.0.
But it's a very good point. That's why we always do the normalization. It's a very good point, Joyce. Go ahead.
One of the major problems we faced was class imbalance. Several asteroid classes were underrepresented, which could hinder their model's performance. We will analyze it in detail later. This part, Iris will present KNN models.
Okay, so for this classical canyon, we just directly do the formula here. So, and we just sampled like 10,000 data set.
Okay.
Yeah. So please move to the next slide. Yeah. Okay, so this is our result, and its accuracy is about. Where's the accuracy of it? Yeah, but it just
0.9. Let me help you. Yeah, 0.9. Yeah.
yeah. Okay, so this is not as good as what we thought. So yeah, move to the next slide. So okay, so I want to sample to the larger data set. Yeah, so the first step, I just considered oversampling and downsampling, yeah, because the imbalance of the data set. Yeah, but for the oversampling, the data set gonna become much larger, and for the downsampling, the data gonna lose a lot. Yeah, so for this balance the situation, I decided to use this smooth ENN. Yeah, but finally it fails. Yeah, because I think it's because of the computational load. Yeah, so because smooth ENN is a hybrid approach combining smooth and edit nearest the neighbors, which is ENN. And this approach is designed to both oversample the minority class and clean up the noise by removing misclassified examples. So for this block, after this, I applied smooth ENN to resample the data. But I proceeded with this method. I found that it wasn't practical for our data set size.
Nice, nice. I never heard about this. It's nice. It's nice. Yeah, go. Yeah, tell me more. Tell me more. Go ahead. Yeah.
Okay, so this smooth ENN increased the size of data set significantly, and our system couldn't handle the resource demand. So it led to slow performance and resource exhaustion. Yeah. So finally, I just directly sampling the data set instead. So I sample it as like a 500,000 data set. Yeah. Okay. So move to the next one. Okay. So this part, we began by scaling our data using a min-max scaler. And this step is essential because KNN is a distance-based algorithm. And scaling ensures that no feature with the larger values dominates the others. So both our training and test data were scaled between 0 and 1. And next, we constructed a pipeline that included 2 steps. Okay, so our first step is feature selection. And we used select k-best with the k-squared scoring function. And the second step is the k-neighbors classifier for the KNN algorithm. Yeah, so as you can see, the k-neighbor classifier, which is in the library, and the k-squared test is a statistical method that evaluates the independence of each feature with respect to the target labels. Yeah, and the reason why I want to select the features is because the data set is pretty large. So I want to like select the fewer features to train the data, to train the model. Okay, and we then use the grid search CV to tune 2 key hyperparameters. Okay, so yeah. Okay, so the result of this, the best K value for feature selection is 10. Yeah, and yeah, I have listed the selected indices. Okay, so for the next slide. Okay, so all right. Okay, so the next part is classical KNN with the Caddy tree. Okay, so okay, so I have improved classical KNN implementation by incorporating a Caddy tree. Yeah, and we chose not to rely on libraries that provide pre-built Caddy tree or ball tree structures, such as sklearn. Instead, we constructed a Caddy tree from scratch, which gave us full control over the structure and allowed us to understand the underlying mechanics of the tree building process.
Very nice. Very nice. Yeah.
Uh-huh.
Go ahead. Go ahead.
Okay, so I'm gonna briefly introduce this Caddy tree class. Okay, so this class is designed to recursively split the dataset along alternating dimensions, creating a balanced binary tree. So each node of the tree contains the data points and labels and pointers to the left and right subtrees. So by using the median of points at each depth, the tree ensures maybe more efficient partitioning of the space. Okay, and okay, so for the next slide. Okay, so yeah, this is my confusion matrix of running this classical KNN with the Caddy trees. Okay, so as you can see, the performance is mostly improved, right? Okay, but because I ran this model locally, and I'm because it can only depend on CPU instead of GPU. But if you install CUDA machine learning stuff, I don't install that. Yeah. So,
it is tricky to get it to work. Yes. Go ahead. It's tricky to get it to work.
it's a little tricky to get that. Yeah, because I use WSL and sometimes it just broke. Yeah, although I have created the environment or I have tried a VirtualBox or something. Yeah, but it just ultimately it just fails. Yeah, but because like my GPU has 24 cores, I think it is.
You're a nerd. You're a nerd. Go ahead. You make me happy.
Okay.
Me happy. Yeah.
Okay, so it basically
just... you still broke the course with the CUDA ML. Yeah.
Okay. So just for the next slide.
So funny.
Okay, and the next part is where it can end. Okay, so firstly, we also use the 10,000 dataset to run this. Okay, so next. Yeah, and this is the accuracy overall. Yeah. So as you can see, just 87, 89, and 89 for the K equals 246. Okay, so next slide. Yeah, so I think this performance is not as good as after implementing the feature selection. Okay, so for the next slides, no, not this slide. The next slide. Okay, wait, the next slide. Okay, so so this is the way it came in after the feature selection, and yeah. Okay, so next slide. Yeah, but I don't know. It's kind of like the because I have encountered the issue after implementing weighted and regularized the KNN. I think it's kind of like overfit. Yeah, but I have selected like about 500,000 data set for this. So I'm also curious about whether it is overfit like this. Yeah. So for K equals 2 and 4 and 6, yeah, you can move to the next slide and the next slide. Yeah, out of them, their accuracy are all 1. Okay, so next slide.
Exactly 1. Wow.
Yeah, exactly 1. Yeah, but like some data points, it's just not on the correct.
Yeah, you can see them as
yeah, we can see that. Yeah, but because I didn't use the libraries like K nearest the neighbors. Yeah, I just
implement from scratch.
Yeah, I just implemented from scratch. Okay, so for the next. Okay, so so this one is regularized KNN. Okay. Apparently this is not my code, but I just can try to explain this. Okay, so yeah, so we use the L2 regularization, and this is applied to the feature weights to avoid overfitting. Yeah, so next one. Okay, yeah. So here's the introduction of voting mechanisms. Yeah, I suppose everybody may know this. Okay, so yeah, I'm not just read this. Okay, so for next part. Okay, so basically, yeah, this is also the 10,000 data set and the confusion matrix. So as you can see, the accuracy is kind of like perfect. They're like 98%. Okay, so for next one. Okay, so for this part is my regularized KNN. Yeah, and so for the first step, if you can see the code, yeah, I have computed class weights. And as you can see here, the ninth class, which is the largest one, yeah, it has the less weight. Yeah.
And the one that goes to 3,000, right? Jesus, that one that is.
Yeah.
The features are also normalized, right? They're also normalized, the features.
Yeah. You mean not normalize the features?
And you do a min-max normalization, right?
Yeah. Okay, so for the next. Yeah, so for this, it's kind of like also perfect for the k equals to 3 and 5 and 7. Yeah. So for next slides and next slides and next slides. Yeah, and the next slides. Yeah. Yeah, and this is the ROC curve for the 10,000 data sets instead of 500,000 data sets. Yeah, so yeah, this is the ROC curve, and yeah. Okay, and this is our 3D PCA visualization. Yeah.
It's not very informative, this one here. Okay, very good.
Okay, so the summary here. Yeah, the data for the data preprocessing, we drop a columns that has too many missing values, and logarithmic transformation and normalization give better comparison of features. Yeah, and so when I was doing this challenge, I just found few challenges. So for the first time, it is the imbalance of the data set, right? And they because it contains about 45 features, if I'm not wrong. Yeah, so I just tried to because I tried to use PCA or something to select the features to just I just forgot the English of that. I just lower the
Dimensionality reduction.
the dimension of that. Yeah. Okay. So look for the last slide. Next. Okay, so this is the feature improvements I have made. So the first one is the sampling method. Yeah, because this data set is pretty imbalanced. So I think the sampling may improve the model. And the second problem is our overfitting problems. So I just trying to figure out why it is matched a lot, even if the data set has up to 500,000. Yeah. Okay, so maybe that's all. Yeah.
Thank you, guys. Thank you. Very good job. Very good job. Yeah. I hope that most people in the call are not getting bored, because for me it's very interesting to see how you guys face, you guys address the different challenges. I hope just you guys are not getting bored. But yeah, it was a good job, and yeah, you're a little bit of a nerd, so I appreciate the nerdiness. Okay, let's take another 10 minutes break. So at 9:30 we come back. We do like half an hour, 45 minutes of class, and I'll let you go. Again, today was 2 hours of presentations. I enjoyed it a lot because I like to hear from you guys. I hope you're not getting bored. See you in 10 minutes. I'll put another baby video on, okay? Ciao.
Hoy llamo café, uno té qua. Mettiamo il latte?
Sì, il latte.
Cosa è?
Ok, scorda. Ok.
Cosa è?
Ok.
Mettiamo il latte,
Ma il latte.
fiamma, tomiamo.
Ok. Zucchero?
Sì.
Non zucchero.
Mettiamo il latte.
Ok.
1, 3, 4, 5.
Brioche. Titi brioche.
Sì, certo.
No brioche.
Siamo anche del latte.
Ok, latte. Latte, caffè. Cappuccino.
Però cotta.
Ascolta.
Mettiamo il latte.
Sì.
Però Però corta,
Ok,
si affiare.
ok, ok. Ok,
Una
Sofia.
corta. Una corta, una corta.
Oh, scuoto, scuoto.
Una corta, una corta.
Ok, ok.
Una corta. Beh, beate 1, 3, 4, 5.
Ok.
Ok.
Titi, pane?
Facciamo pane.
Ok, pane.
Mettiamo latte qua.
Mhm.
Latte qua. Pane.
Dove pane?
Vabbè.
Ok.
Qua pane.
Sì,
Pane con latte.
pane con latte. Ok, grazie.
Così. Sei io, mamma.
Sì, sì.
Ascolta.
Ascolta.
Da
Ok.
mamma no.
Grazie. Ok.
Oh,
Bravo. Brava Titi.
che cosa? Mettiamo pane.
Okay, guys, I hope you appreciated the baby video. I cannot offer anything more entertaining to you guys, unfortunately. My life is not that entertaining at the moment. So let's do a little bit recap of where we were last time, and then we cover some new topics. Let me start my presentation here. How do you do that? View full screen mode. Very good. So we start from here, and then we share this one here. Okay, good. So any comments, you let me know. So again, so next week is the final part on the linear regression for the MNIST dataset. If you have any question, ask Elton. Remember that the MNIST dataset is historical, right? When we will conquer space, right? When we send the next probe to the edge of the universe, we will put the MNIST dataset in there, right? I mean, it has been used probably millions of times by people to test the machine learning models. Every paper starts with an example on the MNIST dataset. And the dataset is very poor now from our perspective, because of course it is a very simple dataset, right? It's linearly separable. You can separate it with a DNN with like 20 nodes, and you know it's not very complex as a task to do classification on MNIST from the current machine learning perspective, but it's historical because it was the benchmark machine learning model for many years. Okay, so that's why it's also a historical value for you to see this. Okay, last time remember we were discussing MMSE. And we discussed we discussed this aspect, right? That if you repeat the training using different subsample data, you get different predictors. Then what you can do is you can have a distribution of the predictors, and this will give you a confidence interval, for example, on the estimation on your prediction. Then we discussed was the multiple linear regression. Remember that we did this example again on the sales from the different sources of information. And remember that then we got to this formula, right? Which is the one that you guys had in your slide today, which is the closed form solution for the MSE. And then, so you see here that that you can calculate the errors, the standard errors in linear regression by this formula, right? X times X transpose to the -1 will give you an estimation of the error committed by the model. This is because of something called the orthogonality principle, which says that, as we were discussing last time, right? So if the linear model makes a prediction, whatever error is left in the prediction, it is orthogonal with your input data. And the interpretation of this statement is as follows. If you have a linear predictor of the data, the linear predictor extracts efficiently in a closed form all the linear dependency between your data and your label. So whatever is left as an error between your prediction and your true label must be orthogonal with the data. Okay, so nothing can be left in the error, which is a linear dependency with the data. Okay, of course, it is useful as a principle, and it has many, let's say, it has many statistical interpretation. But of course, the utility of linear operators is limited, and this is clear to everybody. So the interpretation of this is something like that. If you look at the errors that you commit by the model, they should look Gaussian, right? And they should look sort of uniformly distributed if your model, let's say, if your model prediction was not completely useless. And this follows from the fact that since the model is independent, when we look at the, let's say, at the behavior of the model, let's say, maybe as a statistic, right, as a sum of the model made of all of the over different features or different dimensions, then this summation is more likely to look Gaussian because it's a sum of independent, is sum of uncorrelated samples. Okay, it's sum of samples that from which there is no linear dependency left, and usually the sum. So here we are sort of comparing correlation and independence. So if you have zero correlation, you don't have independence. Independence implies zero correlation. But of course, if we assume again a sort of an additive noise model, then under an assumption of an additive noise model, then the residuals are going to be Gaussian. Very good. Then we discuss collinearity, right? And collinearity is what was also in some of your presentations, and when two features look collinear. So in order to interpret this, for example, we take three models, and the three models you see here that they are described as follows, right? Each of them predicts the sales only from the TV, from the radio, from the news. So what you do is that you do a table like this one, right? So you have a coefficient for all of these different parameters in the model when you have the joint estimation, and you can see how the collinearity operates, right? Because you see that the magnitude of all of them is much greatly reduced when they are pulled together into a single model. Then you want to know, let's say, you want to again do some feature selection. So you want to test the hypothesis whether your features are all relevant, right? Or whether you want to set some of the features to zero. So in order to do that, you do what is called the hypothesis testing setting. So this is a statistical approach in which you say, I have a problem to which I want an answer yes or no. And if I answer yes, then I'm taking the hypothesis null to be true. And if I say no, then I'm taking the alternative hypothesis as being true. So in this case, you set a problem in which all of the features can be set to zero. And this is the model, right? So basically the output is independent from the features that I have. Or you set up the hypothesis in which at least one of the features is not equal to zero. And you evaluate this hypothesis by taking an F statistic that takes the explained variance versus the unexplained variance. How do we define this? So this F statistic is the TSS minus RSS divided by RSS. So TSS is the label I minus the average of the label I summed over all the label i's. Okay, so these are all the labels in the data set. This is the average, and the RSS is the predicted values, right? So for the RSS, you use the linear predictor. So you take the label y and you subtract the predicted label by your model. Okay, so if f is equal to 1, then we take this as an evidence for the null hypothesis is true. So all the features should be weighted with a parameter 0. Or if f is greater than 1, then we consider it as an evidence against 0. Why is this the case? Because this quantity measures the explained variance versus the unexplained variance. Okay, so here this is the variance of the TSS is the variance of the data set as it stands, and from this one here you remove the variance that is explained by the predictor, right? So how much reduction of the data of this is how much reduction is due to the linear predictor, and you divide again by this RSS, right? So if the RSS is only able to predict the mean variance, right, then it's not doing a good job. You're just matching the variance, and f will go to 0. And instead, if the RSS is improving over the mean prediction, then the linear predictor is doing something well. Okay. So then remember that we were discussing qualitative versus quantitative data, right? So we said, for example, these categories, right? These are categorical variables. They take value 0 or 1. You all experimented with this. And what we said is that in linear prediction, you can really see an interpretation of the mapping of the labels into binary values 0 and 1 as having a different model for each of the categories, right? And we give this example of the student credit card budget, Asian versus Caucasian versus African American. And we said, well, we can keep doing this, and we will get to a model, let's say to a different model for all possible combinations. This is not very interesting because, let's say, if you have a category that has 20 possible entries, then you're creating 20 different models. Things are getting more and more confusing. So the interpretability in terms of sub-models is decreased, but of course, it's a perfectly good solution in some scenarios. And then we finished by looking at interaction terms, right? We said, well, if you don't want to look at one feature at a time, or if you, if you think that there are some nonlinear terms that should be inserted in your prediction, what you can take is that you can take the product of the features, and you can treat the product of the feature as a new feature and do the regression over this. And then we said, well, again, the interaction terms have this interpretation as a sub-model, right? That depends on the categorical variables. And we said, well, we can keep doing this. And if we keep doing this, we will get to something like polynomial regression. We said, well, we can just take the interaction terms of features with itself. This will give us a polynomial interpolation, because basically we can treat each power of the feature from 1 to m as a different feature. The linear regression model will still work perfectly, right? So we will have a closed form solution for the parameter b. And since we are at it, what we can do is that we can also take the features to the power of 0, so that we have a constant row of 1s, so that we can write the perfect equation that y is equal to x times y without having a b0 term out. So y is equal to x times beta, and we have a solution for this. And you know, we can also handle polynomial interpolation, interaction term, categorical variable. You can put everything together, and what we obtain is always a solution in terms of these linear coefficients, right? So the complexity of finding the model is very much reduced to a simple, to a linear, to a pseudo inverse, to determining the pseudo inverse. But of course, the issue is that we might still not be able to capture some intrinsic behavior of the data through this manipulation. And when you look at polynomial regression, it is easy to see the effect of introducing these terms, because first we just have a line, right? So if we just take linear regression, we are interpolating data with a line. And as we add more polynomial terms, for example, here this is a polynomial of degree 3, or degree 6, or degree 9, or degree 20, then you see that you are improving the power of your model, but of course, you are running into overfitting issues. So here in these figures here, notice that the red point are the train test, and the gray points are the test set. So you see how the polynomial interpolation, right, matches the position of the red dots. And as the degree gets higher, you see that you lose the ability of the model to interpolate against the trend of the data, and instead you push the model to actually match the position of the data itself. Okay, so of course, a polynomial of degree 10, it's a very specific behavior of the model, so it is possible that some models really need a fitting of a degree 12, but usually as the degree gets larger, the polynomial has this this overfitting aspect where the polynomial starts interpolating the points in the train set itself. Okay, so this is brings us again to the concept of overfitting, which we discussed a few times. We said it's a very general concept that people use almost philosophically sometimes, right? So you can say that sometimes the professor overfits to the class, right? So the professor is teaching to a specific class instead of teaching to the category of students, right? So if we had to come up with a definition, we could define it as the production of an analysis that corresponds too closely or exactly to a particular set of data, and may at a fault fail to fit additional data or predict future observation reliably. Okay. So what we discussed so far is confidence intervals on F, multi-linear regression, interaction terms, and polynomial regression. Okay, good. Any questions on this? Otherwise, we move to the next slide. Okay, if there are no questions, then we continue from here. So let me go into view full screen mode, and I shall share again my window here. Hop, 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 share. So we're leaving here this, and how do we usually spot overfitting? We said that we only have a very expensive way of spotting overfitting, and what we do is that we take the data, we sacrifice 20% of the data to checking for overfitting, right? So we just use part of the data to train, and we use the test to check for overfitting, and we know that when the performance on the test set decreases, then we are overfitting. Very good. So usually you have train and test, and we said sometimes we also save part of the data for training the hyperparameter of the algorithm that we develop, and that one that is what we call the validation data. So the train data is for training the algorithm, the validation is for training the hyperparameter, and the test is for seeing the overall performance. And you can continue this approach ad infinitum, right? So if you have, let's say, a hierarchy of the model where you have a bigger model that chooses a smaller model, that chooses a smaller model, that chooses a smaller model, then this will give you different layers of validation data that you need to use. And of course, this consumes data, right? So in the paradigm of training that we are looking at now, we are just looking at supervised data. And so supervised data, as you can imagine, it's very expensive, right? So the labeling of the data generally is something which is very costly. So people are very careful in adding, let's say, layer of hyperparameters, right? Because it is well understood that you need to reserve data for this, and there is no concept of reusing data, right? There is no concept of being able to use the data for multiple tasks along this hierarchy. I mean, you can do that is a very poor idea, okay? So this, we discussed overfitting, and naturally that leads us to model selection. So model selection is the application of principal method to determine the complexity of a model. That is choosing a subset of predictor that yields the best prediction. And this, for example, would be choosing the degree of a polynomial of a certain model. Okay. A strong motivation for performing model selection is to avoid overfitting, which can happen when we have too many predictors, so that the feature space has a high dimensionality. And for example, a polynomial degree has too high of a degree, and there are too many cross terms that are considered, and all of this give more freedom to our predictor, and if the predictor sort of misuses the freedom that is given to it, in order to produce overfitting, to fit in the data set instead of understanding the trend. Okay. Now we can have a little bit of a discussion here, right? So let's see if I ask you how many different models do you have when you consider J predictors, right? So let's say that we have J predictors, and we can decide to have one predictor for all different possible combinations of models. Okay. So let's say that I have my linear regression toolbox. I'm very happy, but I want to do some feature selection because, of course, I want to reduce the amount of features that I use because I want to simplify my inference. So I start by considering all possible terms, and I decide how many predictors to use. So I can use 0, 1, 2, or 3, and I can choose how many which of these predictors I choose. So if I choose no predictors, I will just always be outputting the mean. If I choose one predictor, I will have a linear predictor with one variable, so it will be a one-dimensional predictor. If I have two, I will have a two-dimensional regression problem. If I have three predictors, I have three problems. And this yields 2 to the j models, okay? In total, I'm going to have an order of 2 to the j models. So selecting the optimal subset of predictors, including the degree of the polynomial, it's tough, right? Because as some of you did already in the challenge, right? You could have a stepwise variable selection. So what you do is that you start from a certain selection of features, you train the model, you test, and you pick one. But in order to see which which degree of the polynomial and which subset of predictor you should use some validation data, okay? So that you use your validation data to select these parameters. And we should also address the fact that when you see a model, you will want to avoid models with very large parameters, because this will create a large variation in the prediction, and this is undesirable, and this is something that we're going to address later with regression. Okay, so one method for doing variable selection that is not exhaustive, right? So it doesn't consider all possible combinations, is to do feature selection. Mean that you start by predicting the mean, then you add one of the features to your bag of currently selected features, and you see how the accuracy over the validation test goes. If you have a good improvement in the validation, you keep the predictor, otherwise you throw it away. And you keep repeating this process of adding one feature to your bag of predictor features at each point in time. And then eventually, after you run through all your possible selection, and you have chosen the number of predictor which is large enough, you will get to the point where adding any further prediction will decrease the prediction over the validation test, over the validation data, so that you choose to stop. And at that point, you would have selected the final subset of your predictors for the model. Okay. Of course, this is a greedy procedure, uses less data, and so you can imagine that at each point in time, you're testing one of the predictors. So you're only going to test one of the predictor once. So the complexity of this will be 2 to the j, right? Because it's as if you have j variables that tell you that the j binary variables that tell you whether you are selected or not. You have j of these, so you have 2 to the j possible combination. And this is much smaller than sorry, this is the exhaustive search. So if you this j square is much smaller than 2 to the j. Okay, so this greedy approach in which you always select whether to add one feature or not, it's much simpler than the full selection. And you can, as you said, we can use you will have to use some validation data in order to do this selection, because then when you go to your client, you will want to just show the performance over the test data. Okay? Very good. This brings us to cross-validation. So let's say that somebody gives us this train test and this validation test, and we start by plotting our few degrees. And we see that a few polynomial interpolation with different degrees. And we use the validation data to see the performance, and since that everything is okay. But the idea is that you are using a single validation set to test among multiple models, and this can be problematic because there is the possibility that you're overfitting the validation set. Okay, so because now you have fixed the size of the validation set. Let's say it's 10% of the data. You have chosen multiple models, and now you're just looking at the performance of the validation set. So if you are testing among, as we said, 2 to the j or j to the 2 models, so like a large set of models, then you run into the problem that while you are rejecting the overfitting of a single model to the train set, it is possible in your selection of the model using the validation set, you are doing overfitting there. So there is no escaping this, right? So this occurs because you have only one single validation set. So what you want to do is to have multiple validation set. What you do is that you randomly split the validation set into multiple subsets, and then you create a prediction of the different models over the kth validation set. And then what you obtain is a distribution of your prediction. And that what brings you joy, right? So if you see a distribution of your prediction, then you are confident. Yeah, you can obtain some confidence intervals, and you can sort of see what is the quality of what is the concentration that you obtain on your data. Okay, so you have a training set, you have training faults, and you have test faults. Okay, so you see that for each of these rows, each of these iterations, we will swap in and out what is the position of the test fault. So the test fault will move from being the last place to the first place for these 10 iterations. For each of these training versus test split, I will generate a model, and I will train the model on the training fault, and I will test the model on the test fault. And then what I do, I look at the performance, at the average performance over the different split between training and test. Okay, so this is called k-fold cross-validation. So you're giving a data set with j features, then to ensure that in every observation data set is included at least one training set, at least one validation set. We do k-fold validation. So we split the data uniformly in C1 to Ck chunks. We create k number of training and validation splits using k chunks for the validation and the rest for the training. Then we fit the model to each of the training set. We evaluate the corresponding performance of the validation set, and then we average over the performance over the validation set. And this is basically cross-validation of the performance. Okay. What is the issue of this? The issue of this is that, of course, we're multiplying our training, right? Now we are, instead of training once, we are training j times. And you guys already experimented with the burden of training multiple models. So it's very, very heavy. Or what you can do is that you can do the leave one night method. So you have the validation set xi, you have the training set x minus I, where you see that the minus side means that you left out one of the element in the training set. Then you feed the model to each of the training set, to f of x of minus I, and then you evaluate on the validation on the I. And then you do the cross-validation score, which is the sum of the I of the performance on the ith sample, right, of the model trained on everything but that sample. Okay. So this is even more extreme because for we are training a number of models which is equal to the data set, right? So this leave one out validation is very, very heavy, but of course there are always occasions in which this is necessary. Then there is the philosophical question, that is, what is the right ratio between test, train, and validate? And this is a very hard test, and you can frame this as, for example, the problem of selecting a degree of a polynomial model, and you have, let's say, x squared, x third, all the way to xm, and you have to choose this for modeling. And and so there is this delicate trade-off between the complexity of the model and the split between training and test and validation. There is no, of course, there is no correct answer, if not as much as possible, right? So it's practitioner's wisdom, is experience. There's many components. So we can go back to our KNN, right? So you remember this plot for KNN, and we said that, well, the hyperparameter of KNN is the K. So here we want to make sure that we use the test data to select the degree. So if K is too small, then the model is too sensitive to noise. If K is too large, then the model tends to produce constant prediction. And what you can do is that we can choose K through k-fold validation. So now we can do k-fold validation for our K equal to 10, and we can see the difference in the performance estimate with no cross-validation and with cross-validation. First of all, you see that when cross-validation, you just get one number, right? So you just get the cross-validation over your validation set, over your test set, so that your estimate of K moves as certainty, right? It has, for each value you have, for each value of K, you only have one scalar. If you had cross-validation, you gain two things, right? First of all, you gain a bar that it gives a distribution of the cross-validation scores. And for this cross-validation score, you can also produce a mean, which is the average of these values. And you see that the length of this bar tells you about the confidence of this estimate. And generally, the prediction with cross-validation differs from the one with no cross-validation. You can see here that the model before picked K equal to 3 as the best model. It is clear that it did so in a way that didn't give us any intuition of the confidence that we had on this decision. But here we can pretty confidently pick 3, And we understand that the uncertainty of picking k equal to 3, it's pretty good, right? It is less than the, for example, k equal to 5. So we might be happier to pick k equal to 5, even if it has a higher RMSE than k equal to 3, simply because the variance is lower. And in many problems, you are much happier to reduce the uncertainty rather than having good performance. Let's say that you have a system, right, when you're producing something for let's say along a production line, like a chain line. It is clear that you will be happier to reduce the uncertainty of the job produced by the machine than to having higher performance. Okay, so especially if you are in let's say in a sequence of operations where having one operation stop will produce a lot of loss, right? You will be happy to the machine, for example, working at lower efficiency if it has a higher reliability. It's something that we're all experiencing with, right? So would you rather have a fast car that is unreliable or a slow car which is reliable? Of course, you're always happy to trade off performance for certainty. Okay, very, very good. Now the bias and variance trade-off. This is what we discussed already, right? So this is the model that we want to have. There is low bias, there's low variance. Model with high variance might have a good average but large variance. A model with low variance and high bias has low variance in the prediction, but it's not very close to the mean. And the worst model of all is high variance and high bias, where our mean is off and our variance is too large. And this is always the goal where we want to live, right? We have the error, we have the model complexity, we have bias, we have variance, and we have total error. Okay, so the variance always goes up with the model complexity. More complex models tend to have more complex behavior that result in high variance, but the bias goes down because more complex models can fit more complex pattern in the data. And the idea is that the sum of these two contributions is what you would call the total error, and the total error has a minimum, which is hopefully unique, that lies somewhere at the intersection of this variance and bias trade-off. Okay, so here we have the usual plot, right? We choose different samples from the data, and we create a linear model from each of the samples from the data. Then we put them all together, and we show that in the linear model things are very much contained. The prediction have very low variance across the different models. Then you repeat the same with sorry, this is a fly. We do the same with a polynomial degree 20, right? And then we repeat the same training of different models with different samples from the data. And we see that when we try to aggregate the prediction of the polynomial model, we have a mess because, of course, the variance of this prediction is so large because the model is overfitting so hard. Okay, so remember this plot when you think about bias and variance trade-off, because this is all you remember. All you need to remember. Very simple models have consistent prediction. Very complex model, they have a much larger variance. Okay, another way to see bias versus variance trade-off is as follows. So when we have the linear model, we can do these violin plots. So we can see what is the average distribution of the B0 and the B1 across the different k-fold validation. And you can see that the values are very, very small. And then if you repeat this with the 20 parameters, then this is going to be a much larger distribution of the coefficients of the 20 different values of the degree 20 regression. So now let's do lasso and ridge, because you partially need this for your project or also for your life. So the idea of regularization is as follows: that linear prediction has many issues and many weaknesses, and we understand this very well now. So what you want to do is that you want to add some regularization term. This will be the term R, and you want this regularization term to depend on the coefficients, right? So you still want your coefficient to take this as into account, and you want to have a lambda, which is your scalar that measures how much you should care for this regularization versus your original objective. So the LB is the usual linear regression, and it's telling you how much error is being produced by these parameters, and then you want to have another term, which is the R of B. We're gonna see next, and then finally you want to have a simple knob, which is this lambda, which sometimes we call Lagrangian for historical reason and reasons that you're going to learn when you do some optimization classes. To manipulate, right, to control how much the function L versus the function R trade-off. So the classical use of regularization is lasso. So what you do in lasso is as follows: you take your loss to be your L2 distance, very nice, and then you add the regularization term that prevents coefficient for growing large. So you add the regularization term which takes the one norm of your vector of coefficients beta. So what you're saying is that through this lambda, we are deciding one unit of RMSE, right, a root of mean square error, should we value, right, for one decrease in the magnitude of the parameters beta. You understand that if lambda is equal to 0, then we just care about minimizing the L2 error. So we just get the linear regression solution. If lambda goes to infinity, then we just want to get a model that has the smallest coefficients possible. And such a model would be a model with all 0 coefficients. So intuitively, this lambda is a sort of an exchange rate, right, between 1 unit of decrease between the RMSE and 1 unit of decrease in the magnitude of the coefficients. And yeah, this is what we will call an L1 norm. Okay, so the first one is an L2 norm, the second one is an L1 norm. Of course, lasso regression, it's a very classical topic, so you can find it in Python, you can play around with it. I'm sure some of you already played around with this. So lasso has a linear scaling of the penalty for large coefficients, meaning that you consider L1 norm. What you can do is that you can also consider L2 norm. And the way to understand this is that the L1 norm looks at the absolute values. So in a sense, scales linearly the loss of the increase of the coefficients. But the L2 norm considers like a quadratic cost. So the penalty for going away from leaving the value 0, it's much sharper. And so there is a higher penalty for larger coefficients. That's why lasso, in a sense, is more conservative than ridge. And this is called ridge regression because you can think that the L2 loss on the coefficient looks like a canyon, looks like a hole, looks like a valley. So it's called a ridge, right? A ridge like a mountain ridge. Okay. Also, this is a classical topic, and you can find in sklearn. You can play around with it. And then there is the choice of the parameter lambda. As you can imagine, this parameter lambda is a hyperparameter, and if there is something that we hate in machine learning, there are hyperparameters. So in order to choose the lambda, you have to save some validation data. You have to be very careful in choosing this lambda, experiment with different lambda, do k-fold validation, pay the price of training k models instead of one models, and everything looks the way it does. But why for lasso there is no closed form solution? Ridge regression has a closed form solution. And the closed form solution is the one that some of you guys already saw. And I just wanted to say this because some of you forgot for the moment linear algebra. And the point is that if xt times x, which is a square matrix, has a certain set of eigenvalues, the effect of this summation of lambda plus I is to move these eigenvalues away, right? Away of a function of a quantity lambda. So there will be a shift on the right of the eigenvalues of a quantity lambda. And the idea of shifting the parameters away from 0 means that when you take this inverse, the eigenvalues of the inverse, which are 1 over the eigenvalue of the straight matrix or the forward matrix, will be further away from 0. So there will be 1 over a quantity which is larger. So they are closer to 0, right? They don't shoot to infinity. If you have a eigenvalue is 0 here, then the eigenvalue of the inverse matrix will be at infinity, and adding the regularization brings back this eigenvalue from infinity to some finite value. Okay? So the idea, the way you imagine this is as follows. So the first function, it's like an ellipsis, right? Meaning that the penalty of moving away from the mean scales like an ellipsis. And the lasso constraint is a constraint on the absolute value. And if we had to represent it on the L2, this will be a diamond, okay? Because here the loss will be 0, 1. This will be 1, 0. So all the points in between will have that the sum of the coefficients will be 1. Okay? And what the lasso minimization does is this: it tries to find a point in which the two functions, they trade off optimally according to this lambda. And so the minimum of the two functions will be, let's say, an intersection of one of the ellipses of this value and one of the points over this diamond. And it does so happen by the magic of mathematics that most of the times the intersection between the two constraints occurs at one of the corners of the diamond. And this also happens in higher dimension. And what happens in one of the corners of the diamond is that a subset of the coefficients are equal to 0. So this is an even better solution than the one that you wanted. Because if you have a solution in which some of the coefficients are multiplied to 0, then you can just drop that parameter, that feature. So the L1 regression, people say that it promotes sparsity, meaning that although mathematically it is not written in the mathematical formula, it often results in the situation in which you intersect one of the corners of the L1 sphere, and this means that some of the coefficients are fixed to 0, and we love setting parameter to 0 because it's simplified operation of the model. Very good. Ridge regression, instead, this constraint is like a circle, right? So all the points in the circle have the same ridge regression. And you see that when you do this, then the intersection is not going to be one of the corners. So although ridge regression is preferable because it has a closed form solution, it doesn't generally result in a sparse model, in a model where some of the coefficients are 0. That's why left is harder but more desirable. Right is easier but not as desirable. Okay? You can work through this, no problem. And I think we stop here for now. Just some aspect for you and some memes for you. And I think we stop here for now. And then next time we're gonna move to, I think we're gonna move to the topic of, let me check a second the schedule. Yeah, we can do some cross-validation and model selection. We did it today. We can do some PCA. I think we can move eventually to PCA. I think it'd be nice so that you guys see some dimensionality reduction techniques. And then remember that next week is the final presentation. Then you have the third challenge. And then after that, you can choose your groups as you want, okay? So you have to bear with the random selection of the partner just for one more challenge. Well, I think now everybody gets to know each other. Everybody is making friends, is getting to know the strengths and the weaknesses of the different people in the team. So I think that'll be great. Okay, so I'm going to mute myself. I'm going to be here for 5 more minutes if you have questions. And otherwise, I'll see you guys next time.